In this video, we're going to be talking about commutators of our operators in quantum mechanics. Commutators are very important, so let's learn how to find some with some given operations. So here we have two different operators, A and B, where A is just the first derivative and B is just the first derivative plus 1. Let's see if these operators commute, where AB minus BA is equal to 0. Or basically this just says, is the operator of AB on our function the same thing as BA on our function? So that's what we're going to do. First, we're going to apply B, then A. So A times B applied on F. So the way that you read this is that B is applying its transformation on F first. Then whatever that results in, you're going to apply that transformation from A onto that resultant. So in order to actually apply this, A is going to be applied second. So here we're going to have d over dx applied onto B, which is d over dx plus 1. That applies onto our f of x function. So what this will result in is we'll have d over dx applying on df over dx plus f. And we can end up distributing out our derivative as well, where now this is going to be the second derivative of f with respect to x plus the first derivative of f with respect to x. So that is AB applied onto f of x. Now let's find BA of f of x. So this is the opposite, where A is applied onto f of x first. So here we're going to have d over dx plus 1 applying onto d over dx that's applied onto f of x already. So I skipped the step from the first one, where f of x has already been applied by the first derivative. So now if we distribute our operators here, in order does matter. D over dx is just the same thing as saying d over dx squared when you distribute it of our function here. And now we have our identity operator, or plus 1, where it's the same thing as saying 1 times the first derivative, where we end up with the first derivative again. So we see we have the same resultant, AB of f of x is the same thing as saying BA of f of x. When you find your commutator here, it's the same thing as trying to find AB minus BA. AB and BA are relevant to what we found above, where now AB is just everything after we factor out our f of x. So AB is the same thing as saying the second derivative transformation plus the first derivative transformation. And the same thing for BA. BA is going to be the second derivative transformation plus the first derivative transformation. So when we plug that into our AB minus BA, we end up getting 0 for that case. And this means that these operators do commute. And that's going to be very important, especially in quantum mechanics with something called the Heisenberg uncertainty principle. Before we move on to more problems, please show your support for this channel by liking and subscribing, as all I want to do is help support students on their learning journey. Let's look at another problem. So this is going to be more application-based, where we have a position and momentum operator, and this is very important and a very common example. Here, the question is asking, can both these observables of these operators be measured simultaneously with unrestricted precision? And what this means is that does the commutator of x, of p of x, equal 0? If it equals 0, then this statement would be true. We can measure them simultaneously without any restriction. But we need to find this actual commutator. And these will both have our little hats on it as well. So here, we're going to check x of p of x. And this is going to be the same thing as saying x applied onto p of x. That's been applied already onto our first function, minus p of x applied onto our x that's already been applied. So let's look and try to find x p of x first of an f of x function. So here, we're going to have x, which is our x operator, multiplied by minus ih bar d over dx that's applied already onto our f function. So when we simplify this out, there's no any sort of extra operations that we need. We have our constant minus ih bar multiplied by x df dx. So when we factor that out, it's the same thing as saying minus I h bar x d over dx when we factor out that f of x function. So let's look at p of x applied second, and then our x applied onto our f of x function. So here, we're going to have minus I h bar d over dx. That's going to apply onto x times our f of x function. This is very important, and this is where most students make a mistake. So don't be one of those students. Here we have a derivative of this function here. Our minus I h bar is constant, so that distributes out. The derivative of two functions of x will result in using the product rule, where we have to take the derivative of one of them and retaining the other, and then add it to the opposite result. So here, it's going to be x times df over dx plus f of x times dx over dx, which is just 1. So this is where an extra step will be needed, and most students will miss that extra step. And so when you end up factoring out our f function, the order of these operations do matter, and this is the reason why, is we'll end up having minus I h bar x times the first derivative plus 1. That is going to be our pxx operator. So now when we try to find the commutator, we're going to subtract those two things together. So x px minus px x is the same thing as saying we're going to factor out minus I h bar for all of them because they contain it all. Then x px is x d over dx minus the quantity x d over dx plus 1. And so when we cancel out our x dx, because they're two of the same terms, we end up getting that the commutator x p of x is just equal to I h bar. So we have a negative 1 out here that ends up making the front term positive. So this has a non-zero commutator, which means the answer is no. We have some sort of uncertainty when we measure both position and momentum. And that's going to be common throughout all of your quantum mechanics class. And it's the same thing if we look at like energy versus time. So let's move on to one last problem. First, we're going to try to find the commutator AB and then also B of A to see how they actually end up relating to one another. And it's actually a very simple relationship, but it's also a good way of actually checking ourselves. So here we have A and B, where A is just multiplying our x squared function, and B is x squared multiply the first derivative. So we know AB is the same thing as saying AB minus BA. So let's find AB of x, or AB of f of x. So A is just going to be x squared multiplied by x squared df over dx, which is the same thing as saying x to the fourth multiplied by the first derivative of f. And so when we factor out the f function, we see that AB is equal to x to the fourth times the first derivative. BA, applying onto f of x, is now a little bit opposite, where we have x squared d over dx applying onto a function x squared f of x. Now again, this is where we have a derivative of two functions of x squared and f of x, so we're going to have to apply the product rule. 99% of the time, you'll have to use the product rule for functions that do not commute, so keep that in mind. So we're going to have for x squared, that's the front term, that doesn't apply into this derivative, multiply the derivative of our two product functions. We'll end up taking the derivative of the first function, where we'll get 2x multiplied by f of x plus x squared times f prime of x, or df dx. And so when we factor that out, we'll end up getting 2x cubed multiplied by f of x plus x to the fourth d over dx applied onto f of x. And so when we factor out our f of x, we'll end up getting multiplied by 2x cubed plus x to the fourth times the first derivative. So when we look at the commutator A B is the same thing as saying AB minus BA, where AB is just x to the fourth d over dx minus the quantity 2x cubed plus x to the fourth d over dx. So when we cancel out our x to the fourth d over dx, we'll end up getting the commutators minus x cubed, or minus 2x cubed, sorry. And now if we look at our commutator BA, it's just going to be BA minus AB, which just appears to be the negative of this result above. And let's show that to be the case. We'll end up getting 2x cubed plus x to the fourth d over dx minus x to the fourth d over dx, which will result in a positive 2x cubed, and it's the same thing as saying minus a b commutator. That's an important result to understand as well with the commutators. The commutator of two operators is just equal to the negative sign of the reverse of that commutator. So just keep that in mind. I hope you have learned something today about our operators and commutators. Please comment down below if you have and any questions you may have, and have a great day.